Okay, so we're asked to prove the given proposition, which is if P is an odd prime, then P minus 1 factorial is equivalent to minus 1 mod P. And just to recall, the way that the factorial is defined is if you have K factorial, that means it's K multiplied by K minus 1 multiplied by K minus 2 multiplied by so on all the way until 2 times 1. Okay, and so to start off, what they want us to do is to find the inverse of A mod 7 and provide each inverse as an integer between 1 and 6. Okay, so typically, like if there's like the last few questions on the exam, they if it's like a slightly more complex, then they break it down, and so that each little problem is supposed to help build you up towards the like it's gonna be helpful in the proof later on. Okay, so let's do this. So they want us to find the inverse of A mod 7. So you have the inverse of 1 is always going to be 1. The inverse of 2. So if you have 2 multiplied by something mod 7, this needs to be equivalent to 1. If it's when it's equivalent to 1, then this thing is called as an inverse. So it's gonna be a simple plug and check method. So if I had 1, so 2 times 1 would be 2, wouldn't work. 2 times 2 is 4. 4 minus 1 is 4. 2 times 3 is 6. 2 times 4 is 8. And then 8 minus 1 equals 7, right? So 2 times 4 works, which means the inverse of 2 is 4. And then you have that the inverse of 3, inverse of 3 is okay, so you have 3 multiplied by something mod 7 should be equivalent to 1. So 3 times 2 is 6. 3 times 3 is 9. 3 times 5 is 15. So this would work because 15 minus 14 is equivalent to 1. So 5 is the inverse of 3 mod 7. And then we've already looked at the inverse of, if you have the inverse of 2 mod 7 is 4, then the inverse of 4 mod 7 is 2. Like it goes both ways. Inverse of 5 is gonna be 3, and then inverse of 6 is gonna be, um, so you have 6 multiplied by something must be equal to 1 mod 7. Yeah, so let's think. You have, so 1. 6 times 2 is 12. 6 times 3 is 18. So 4 is 24. 5 is 30. 6 times 6, okay, 6 times 6 is 36. 36 minus 35 is 1 mod 7. So the inverse of 6 is 6 mod 7. Okay, so we were able to find the inverses. Now they want us to show that the proposition holds when P is equal to 7. Okay, so what's the proposition again? Is if I have P minus 1 factorial, that must be equivalent to minus 1 mod P as long as P is prime. So P minus 1 factorial is basically 6 times 5 times 4 times 3 times 2 times 1 mod 7. Okay. So now we could multiply this out and then we would probably get an answer. And then maybe if we like simplify it, we might realize this is minus 1 mod P. But the fact that they've asked us to calculate the inverse in part A means that it's going to come in handy, right? So it's going to be useful to use this information in trying to figure out what P minus 1 factorial is. Okay. Um, so we know that um, okay. So I know that the inverse of 2 is 4, right? So if I multiply 2 and 4 under mod 7, that must simplify to a 1. And similarly, if I multiply 3 and 5, that must be a 1 again. Okay, so we can use that information. So 5 and 3 essentially cancel out because they're inverses. And then we have 2 and 4 cancel out because they're inverses. That's going to leave us with 6 mod 7. And 6 mod 7 is just minus 1 mod 7. And so we have proven the given proposition. Okay. Okay, so note that in part A, the only values that are their own inverses are 1 and p minus 1. Yeah, which is what we saw. With every other example, the inverse was some other number. And this is true for any prime modulus p. And you can use this fact without proof. Now prove that for any odd prime p, we have p minus 1 factorial is equivalent to minus 1 mod p. Okay, so we can use some of the intuition that we developed from part B, right? So if I'm writing out p minus 1, instead of having to multiply the elements or multiply the numbers, I know that a few of the numbers are going to cancel out with each other because they're not gonna because the inverse of that number is not going to be itself. It has to be some other number that I'm multiplying it with. So that's gonna simplify down to a 1. And that's the case for all of the numbers except for 1 and p minus 1. So ultimately we're gonna end up with p minus 1 mod p, which is minus 1 mod p. So I guess that's gonna be the entire proof. So let's write it out and see how that goes. So I need to show that p minus 1 factorial and compute this. So I know some students typically, like students sometimes get the urge to say that this is equivalent to minus 1 mod p, and they kind of work, and then they keep the minus 1 here throughout. But just a reminder that we cannot do this because I don't know that this is equivalent to minus 1 mod p yet. So I only bring this at the very last step of the proof. I know my goal is equivalent to minus 1, but I cannot say that it is already equivalent to minus 1 mod p. Okay? Okay. So we have p minus 1 factorial. P minus 1 factorial is equivalent to p minus 1 multiplied by p minus 2, p minus 3, so on until 2, 1 mod p. Okay? And then we're gonna say, um, since for any number between p minus 2 and 2, well, I guess this isn't any number. We could say for any integer between p minus 2 and 2, um, we have, yeah, since for any integer between p minus 2 and 2, its inverse is another number also between p minus 2 and 2. We can fully pair up all the integers in this range. We can fully pair up all the integers in this range um, such that when multiplied, um, this is equivalent to 1 mod p. So then I have my p minus 1 factorial is equivalent to 1 multiplied by p minus 1 multiplied by the 1 that is by multiplying out all of the numbers with its inverses. Okay? And so this is p minus 1 mod p we know is equivalent to minus 1 mod p, which is what the proof asks us to prove.